So hello everyone. Today I am going to start the next topic, that is agitation. So as we have discussed earlier, in the case of gas liquid mass transfer, both aeration and agitation are very important. So aeration part we have already discussed. In fact, in the last lecture we discussed how to experimentally measure the mass transfer coefficient KLA. So today we will be discussing mixing part. What is mixing? What are the different component of mixing? Then power requirement for the mixing. So in the last lecture we discussed the experimental methods to determine mass transfer coefficient KLA. So we discussed oxygen balance method. You measure the pressure of oxygen at inlet and outlet. We consider dynamic method, that is you have to first degas the system, then again you have to regas. And then sulfite oxidation method, here sulfite is oxidized to sulfate by uptaking the oxygen. Now today we will be starting with empirical correlation for KLA. In the last lecture we discussed experimental methods. Today we will start with empirical correlations. Then we will go to the next topic, that is mixing, then power requirement, and then how do we calculate mixing time. So before we proceed for this empirical correlations, because there are certain dimensionless number, so we will quickly revisit these numbers which are relevant here. The first one is Reynolds number, which is defined as inertial force upon viscous force, and the formula is rho of density of liquid, velocity and diameter rho Vd upon mu. Next is Schmidt number, which is defined as momentum diffusivity divided by mass diffusivity. So momentum diffusivity is related to viscosity and this mass diffusivity is related with diffusion coefficient, so rho L into dAl. Next number is the Sherwood number, which is defined as overall mass transfer rate divided by diffusive mass transfer rate. So overall mass transfer rate is KL d into P dia of the particle divided by diffusive mass transfer rate dAl. So this number is very important, KL. If you know the value of NSH, it's equal to KL dP upon dAl. So from here we can find the value of mass transfer coefficient KL. Next number is the Grashof number, which is defined as gravitational force upon viscous force. So gravitational force is defined as gravitational constant dia of particle to the power cube density of liquid minus density of particles divided by density of liquids divided by viscous force mu L square. Now the first correlation, so as the word suggests, correlation means these relations are based on the experimental data. So we will be quickly discussing this Mu-Young correlation. So it is depending on the size of bubble. So if the bubble size is less than 2.5 millimeter, so it says NSH is Sherwood number equals 0.31, Grashof number to the power 1 by 3 and Schmidt number to the power 1 by 3. And what is NSH is KL KD upon dA diffusivity. So here we get the value of mass transfer coefficient. And for the large size of the bubble, the similar correlation is there. It says NSH equals 0.42, Grashof number to the power 1 by 3 and Schmidt number to the power now 1 by 2. This has been little change here. Further, there is a correlation based on the energy input. So the PT is total power dissipated or power required for the mixing operation. And once you are mixing, there will be UG is defined as superficial gas velocity, which is defined as volumetric gas flow rate divided by cross sectional area. So, velocity UG is defined as F upon A. VL is the total liquid volume. So, it says KLA, power mass transfer coefficient, is proportional to PT upon VL to the power alpha and superficial velocity to the power beta. So, it is directly proportional to power requirement, directly proportional to superficial velocity, and inversely proportional to the liquid volume. And alpha and beta are the constant ranging in the range of 0.2 to 1. And when you are having this for viscous and non-Newtonian fluid, so non-Newtonian fluid means viscosity value is not constant. So, there we are going to add one more term, apparent viscosity. So, here this will be proportional to Pt upon Vl to the power alpha, superficial velocity to the power beta, and apparent viscosity to the power minus delta. So, in this way we define this KLA based on what is the power input required. So, for example, if you just see stirred vessel for water air dispersion and coolizing system. So, KLA is defined as P upon V to the power 0.4 and UG to the power 0.5, and this correlation is applicable if total volume is less than 2.6 kiloliter and power requirement between 0.5 to 10 kilowatt per meter square. Similarly, if stirred vessel water and if it is not coolizing system, then the P upon V to the power 0.07 and superficial velocity to the power 0.2. So, the value of alpha and beta is changing, and this correlation is valid for the volume in the range of 2 to 4.4 kiloliter, and power requirement is the same. Similarly, for bubble column, for superficial velocity in the range of 0 to 0.15 meter per second and Pg upon V in the range of 10 to 1100 watt per meter cube. So, there is a correlation, it says KLA as 0.08 Pg upon V divided by 800 to the power 0.75. So, this is for the bubble column, and here Pg upon V can be further calculated based on this correlation. It says Pg upon V equals 800 into Vs superficial velocity divided by 0.1 to the power 0.75. So, what we discussed here is this KLA can be determined if the hydrodynamic parameters are given to calculate total power requirement, volume, superficial velocity, and if you want to calculate this cross up and estimate number, so you require the viscosity and diffusivity, like this density is also required. So, if these parameters are there, density, viscosity, diffusivity and particle size, then we should be able to directly calculate the KLA value based on the empirical correlations. Otherwise, one can always go ahead with experimental methods. Now, we will go to the mixing part. So, agitation. So, this is performed particularly in the suspended cell fermentation to mix three different phases. The objective of mixing is to mix three different phases in bioreactor. Particularly, what are three different phases? Most important is gas, liquid and solid, because there is both heat and mass transfer takes place. So, gas phase mostly oxygen and carbon dioxide, There may be other gases as well. Liquid phase, we consider the dissolved nutrients, metabolites and fermentation broth or media, and solid phase we consider cells as well as some solid substrates if it is solid state fermentation or if you are dealing with immobilized systems. Then what is the objective of mixing? It should produce homogeneous condition and promote both mass transfer of nutrient and gas as well as effective heat transfer to maintain the optimum temperature. So, the aim is to enhance transfer into liquid from the gas phase, the first, then prolong the retention of the air bubble for the better mass transfer, reduce the bubble size to increase the surface area for oxygen transfer, prevent bubble collisions and decrease the film thickness at gas liquid mass transfer, because this thickness is imposing maximum mass transfer resistance. So, what it says, this agitation is very much complementary for effective aeration. In addition, so it says if you go for better mixing, or you can say if you go for higher rate of mixing, then it will be better aeration, but at the same time it imposes the shear, and high shear it can damage the shear sensitive cells, and if there is a low shear then it causes cell flocculation or unwanted growth on the surface. So, we require this suitable shear condition during the fermentation, so that this agitation should lead to the effective aeration. At the same time, it should not damage to the shear sensitive cells. Particularly, this animal and plant cells are much more shear sensitive. The applications we can quickly summarize now. To blend the soluble components of liquid media such as carbon source, disperse gases through the liquid in the form of a small bubble, maintain the suspension of solid particles such as cells and cell aggregates, and wherever necessary disperse immiscible liquids to form emulsion or suspension of fine droplets. And in addition to the mass transfer, the promote heat transfer to and from the liquid medium. So, you can quickly see this one mechanical agitated vessel. So, there are three components: baffles, impeller, as well as you can see there is a specific shape of the base. So, what is the role of baffle here? They reduce the gross vortexing or swirling of liquid. And what is the role of impeller? To pump the liquid and create a regular flow pattern. So, baffle, impeller and the base, it should be rounded at the edge rather than the flat. This eliminates the sharp corner and pockets in which fluid current may not penetrate and discourages the formation of stagnant zone. So, the shape of the base is important to avoid this stagnant zones. In addition, you can just see there are three ways the baffle can be attached: directly from the tank wall, slightly away from the tank wall, and at certain degree or inclination. So, baffle attached to the wall particularly for low viscosity liquids, and as the viscosity increases for moderate viscosity, baffle set away from the wall for moderate viscosity liquid, and baffle set away from the wall and at an angle for high viscosity liquid or the fluid containing suspended cells or particles. And typically what is the clearance here? It is defined in the relation with the tank diameter. So, it is 1 upon 50 times of tank diameter, 1/50th of tank diameter. Now, we will quickly see the how the agitation takes place. The first one is in the case of stirred tank reactor. This is most common and widely used. So, there the part is the impeller, which is connected with the external motor driving the stirrer system. So, this impeller, this is this impeller shaft, and this impeller shaft will be attached to a motor. So, once you are having multiple openings, here it is important we need to seal, but certain openings will be required for that inlet of air or for the sampling port, exit of the air, and in addition sometimes if you are able, if you need to operate in a fed bias mode, there should be inlet for the media. So, we typically this up to 3 inlets are recommended, and for the effectiveness of agitation it depends on the design of impeller blade. So, there are different type of blades we will be discussing in the next slide. What is the speed and what is the depth of the liquid. So, these three are very important parameter, which type of impeller, what is the speed, and what is the depth of the liquid. Here I have summarized a few design aspects for this stirred tank bioreactor. So, typically aspect ratio height to diameter varies between 3:1 to 4:1. Height of liquid to the diameter is 1 to 1.25. So, you just see there will be enough head space, and diameter of impeller to tank diameter is 1/2 to 1/4. And in addition there is a clearance from the base where these impellers are installed from the bottom of the reactor. It is 1.6 to 1.2 times of diameter. Number of baffles, typically it is 4 to 6, and width of the baffle is 1/10 of the vessel diameter, and the function of baffle and impeller we have already discussed in the last slide. Other system is this pneumatic system. It is very similar to this airlift bioreactor. So, it does not have any moving part. It uses the expansion of the compressed gas. So, you just see the sterile compressed gas is entering here, and once it is entering here, the gas will go upward, and further because of change in the density, it will try to recirculate on its own. So, here this compressed gas and its flow rate is very important for the pneumatic system. So, it does not require any external power, and the air bubble expands in the riser, and the further they go for the cycling due to density difference. Here another method is the to improve the performance of pneumatic system further, you can have an external pump for the better recirculation. So, use kinetic energy for the mixing by external pump for circulation and re-injection. It is circulating and it is re-injecting. So, we have to increase the turbulence. If you increase the turbulence, you can achieve the better mixing. So, here there is a challenge here, typically one end up with non-uniform condition because of this pumping arrangement, and the vessel greater than 500 liter capacity. So, it is good for the smaller vessels, but for larger scale typically we go for this stirred tank bioreactor. Now, another component for the mixing is the spurger, as we have discussed in the aeration topic as well. So there are different type of sparges. It can be porous. This is made of sintered metal, glass or ceramic, particularly used in small scale, but there is always risk of blockage by cells. Next is the orifice or perforated pipes. So they are the ring shape or the cross shape. Their larger hole reduces the blockage. They are used in the production of yeast, single cell protein and wastewater treatment. Now next one is the nozzle. So it can be single open or the partially closed pipe. In addition, this knowledge have the provision for the injecting two phases. So this imposes this low flow resistance, low blockage risk, and widely used. The nozzles are widely used for the sparging. There can be other designs, as I told, this two phase ejector injector, where gas and liquid are pumped together through a nozzle in order to generate tiny bubbles, and this combined sparger agitator like hollow stirrer shaft delivers air. And it is very important that all designs should allow for in place cleaning, means in place sterilization, to avoid contamination in the bioreactor. So here you can include a few pictures. You can just see this is a deep tube, this is a perforated tube, you can see perforated tube, this is the perforated ring, this is a ring shape, it has perforated, and this is a porous plate. And in addition, one can have this complex two phase injector devices where either liquid is coming from the center, gas from the outside, and depending on the nozzle you can see there is a different type of flow pattern. So one, it can be broadly divided into compressing as well as in the non-compressing system, and it operates based on the Bernoulli theorem. Now we can achieve different flow patterns. So rotational flow, if the flow is around the stirrer shaft; a radial flow, if the flow is from the central axis out to the side of the tank and back again; and axial flow, if it is up and down the to the height of the vessel. You can just see this is the circular flow, or you can say rotational flow. This is the radial flow, and this is axial flow. In addition, depending on the gas flow rate and stirrer speed, so there should be a good balance between these two. If there is a high gassing rate and low stirrer speed, it means stirrer is unable to disperse and retain the gas bubbles, so it leads to the impeller flooding, means all the gas will go out of the bioreactor quickly. Second is, if stirrer speed is increased and gas flow rate is reduced, this is called the impeller loading. It means the sufficient gas is not available, and at a higher stirrer speed and this low gas flow rate, so the stirrer speed is sufficient enough to disperse and retain the gas bubble, and this results in a complete gas dispersion. There are three terms: impeller loading, impeller flooding, and complete gas dispersion, and that depends based on the gas flow rate as well as the stirrer speeds. In addition, there is one more term that is called solidity ratio. This is equals to the projected blade area divided by the area of the circle swept out by the impeller during rotation. So you can see this is this projected blade area and this circle enclosing the impeller sweep area. Now there are different type of impellers. So, the choice of impeller depends on the liquid viscosity, the level of turbulence required. So, we can classify in terms of propeller, paddle and turbine. These are the three broad category: propellers, paddle and turbine. It depends on their design patterns. So, you can just see the propeller directly on the axis or the shaft. These blades are attached, that is called the propeller. In the case of paddle, there will be axis, and in the case of paddle, in the shaft you need to have another rod, and there you can attach the blades. So, this is very simple to the you can correlate with the paddle of a cycle. And next is turbine. So, turbine says this is your shaft, you are going to have another plate, and there you can have the multiple blades. So, you are going to have another circle pathway, then let us say for example 6 flat bed disc turbine, or this is a pitched blade turbine. So, apart from these three propeller, paddle and turbines, there are certain other special impellers, particularly anchor, gate anchor, the helicals, and they are used for the high viscous fluids. Particularly if you want to handle the solid powder particle, one need to go for the helical screw. So, here I have presented this impeller type and viscosity range. This is in the centipoise. So, you just see for the low viscosity, this low to medium viscosity propeller and turbines are much suited, and for the high viscous, this helical screw and helical ribbons are recommended. Further, here you can see, depending on different type of impellers, what is the pumping requirement and what is the turbulence generated. So, for the turbine, you just see the turbulence dispersion is in the desired range, and also it requires less pumping. But at the same time, if you go for the helical ribbons which handles the high viscous fluid, the turbulence is still less and pumping requirement is much higher. So, depending on the what is the fluid viscosity, you have to choose which type of impeller will be most suited. And how mixing is done? So, for the large liquid circulation loop forms in the stir tank, and it is necessary that impeller flow must sweep entire vessel quickly for the effective mixing and avoid any stagnant or dead zones. And there are three mechanisms. One is distribution, dispersion and diffusion. So, distribution means it is a kind of a macro mixing, the bulk transport of material by circulating currents. Dispersion, now it break up the bulk into smaller eddies, it can be macro or micro mixing. And diffusion, this is a micro mixing, this molecular level mixing within smallest eddies. Now, depending on the which type of impeller we are having and which type of flow pattern is there, this mechanism of mixing will prevail in a bioreactor. Now, next quickly we will go through the power requirement. Impeller, we need to have this external motor for its rotation. So, it requires a huge amount of power, and the range is from 10 kilowatt per meter cube for a small vessel to 1 to 2 kilowatt per meter cube for the large vessel. And typically power is related with the torque like this. So, P is the power, Ni is the stirrer speed, M is induced torque, and now there can be three different arrangements in the stir tank. One is ungassed, there is no aeration, only agitation, Newtonian fluid. Second will be ungassed non-Newtonian fluid, and third will be the gassed fluid. So, we will start with for ungassed Newtonian fluid for the power requirement, then further we will stop at the gassed fluid where both aeration and agitation will be present. So, for ungassed fluid, the power requirement depends on the stirrer speed, impeller size or diameter, tank geometry, fluid density as well as fluid viscosity. Now, there are certain terminology which we need to understand in the case of power requirement, particularly the comes the Reynolds number. As we have discussed, Reynolds number is defined as rho v d upon mu. Now, in the case of impeller Reynolds number, this velocity is replaced by n into d. N is the RPM and d is the impeller diameter. So, d is proportional to di is proportional to tank diameter. So, this diameter is also replaced by the di. So, it becomes rho into ni di square upon mu. So, in this way we calculate the impeller Reynolds number. Now, coming back to power requirement, so it is defined as in terms of power number. So, first we need to understand what is power number. Power NP. Power number is defined as P divided by Ni cube di 5 into rho. So, Ni is the RPM or stirrer speed, di is the impeller diameter, rho is the density. So, from there we can directly, if power number is known, we can calculate this power as NP, only power number is required, density is known, Ni cube, impeller speed is known, impeller diameter is known. So, if power number is given, we can quickly calculate the power requirement. So, power number, it has been tabulated based on the experimental data for different type of impellers, and that is available in the textbooks. Now, if we increase in the Reynolds number and power number, how it varies. So, you just see in the case of turbulent fluid region, power number is constant, but in the case of laminar region, it is following a linear trend and followed by transition and turbulent. In addition, it is important to note one is Ruston turbine, two is pitched billet turbine, and third is marine propeller. So, for different type of impellers, you can see there are different curves here. It means the power number varies based on the flow rate as well as based on the type of impellers. Now, for different type of impellers, you just see the power number is given here. We will focus first on turbulent flow. For Ruston turbine, it is 5, for pitched billet turbine 1.3, marine propeller 0.35, anchor 0.35, and helical ribbon 0.35. So, straightforward for this turbulent flow, we can calculate. Now, what is happening here in the case of laminar flow? There is a linear relation between power number and Reynolds number. So, it says this power number is inversely proportional to the Reynolds number. So, what happens? Let us say P equals NP rho Ni cube di 5, and this is inversely proportional to the Reynolds number. So, we divide by the Reynolds number 1 upon Re. So, it says P proportional to 1 upon Re. So, it becomes Ni di square rho upon mu. So, rho is cancelled out, mu will go in the numerator. So, it becomes P as NP to mu. Now N, this will be Ni square and this will be Di cube. And as the NP is coming out to be same, so here either we write NP dash or many times it is written as K1. So for the laminar region, P is written as K1 into mu Ni square Di. So we have discussed this for laminar region, power number is inversely proportional to Reynolds number, and for turbulent region it is constant of the Reynolds number. So here I have listed one example. It says the fermentation broth with viscosity of 10 to the power minus 2 Pascal second and density of 1000 kg per meter cube is agitated in a 50 meter cube baffled tank using marine propeller 1.3 meter in diameter. So propeller diameter is 1.3 meter. Calculate the power requirement for a exterior speed of 4 second inverse. So first you have to calculate the Reynolds number. So it is given as Re as Ni di square rho upon mu. The density is 1000 kg per meter cube. Viscosity is 10 to the power minus 2 Pascal second. Di is impeller diameter is 1.3 meter. So we will calculate the Reynolds number and it is coming out to be 6.75 between 10 to the power 5. It means this is a turbulent region. And now for the marine propeller in the turbulent region, the power number is 0.35. So power number we have got 0.35, and for turbulent region this is the formula we have already discussed, NP into rho Ni cube Di5. All the parameters are known. If you put here, you will get the power requirement as 83 kilowatt. Now next case comes in the fluid is non-Newtonian, the ungased system and non-Newtonian. So as you know this how this viscosity is defined. So we are going to define apparent viscosity like this. Viscosity is defined as a ratio of shear stress divided by the shear rate or velocity gradient. Now for the apparent viscosity what we are going to write is a constant K into shear rate to the power n minus 1. So in this way we are going to modify it, and see how shear rate is defined. Shear rate depends on the RPM, small k constant into Ni RPM. Now when we defined Reynolds number Ni di square rho upon mu, now this mu will be replaced by the mu apparent. What is mu apparent here? It becomes Ni di square rho, and mu apparent will be defined as capital K, and this shear rate is replaced by small k Ni to the power n minus 1, and if we rearrange it, Ni will go up, so this will be 2 minus n Ni to the power 2 minus n di square rho upon capital K small k to the power n minus 1. So in this way we calculate the modified Reynolds number. Now further what we are seeing here is, it's very interesting to see for the Newtonian and non-Newtonian fluid only the change is observed in this range. If the Reynolds number varies between 10 to 100, then only you can see there is a different pattern for the non-Newtonian. Otherwise in Reynolds number less than 10 or greater than 100, it is following same pattern for Newtonian as well as non-Newtonian fluid. So if Reynolds number is not falling in the range of 10 to 100, then we can directly calculate following the calculation what we discussed for the non-Newtonian fluid. Only in this range we have to calculate this modified Reynolds number, then we need to read the value of power number and we have to calculate the power requirement. Now the last system is the gas fluid. So in the case of gas fluid what we are seeing is it is agitation is there. Along with that we are also considering this aeration part. So once the aeration part is there, it means some of the mixing will be done by the aeration. So the power requirement for the agitation will decrease, but some power will be required for the aeration. So first there is one term that we will be discussing is gas flow number. FLG, it is defined as gas flow rate, volumetric gas flow rate divided by stirrer speed into impeller diameter cube. So here you just see gas flow rate versus you have to plot Pg power requirement in the gas system divided by P naught power requirement in the ungas system. So as the flow, the why flow number is coming because of the volumetric gas flow rate. You can just see that as flow number is increasing, there is a decrease in the Pg upon P naught value. It means Pg value is declining, and from this curve you can just see it declines, and after certain value of power number it reaches to the plateau. Here again similar to the ungas system, this trend vary for the different type of impeller as well as for the different RPM. For example, this NI open circle correspond to NI of 120 RPM, closed circle correspond to NI of 150 RPM, and this closed square correspond to NI of 360 RPM. So what we have to do here, we have to first calculate FLG. Second step is to calculate Pg upon P naught ratio, and if you know the ratio, third step is you have to calculate the P naught, then you fourth step is you multiply Pg upon P naught into what is the ratio you are getting over here. So this is the power requirement for the stirrer or agitation. So you can see this power requirement, it gives 40 to 50% reduction in the agitation or stirrer power requirement, but in addition you also have to calculate the power input for gassing, because there will be power requirements and it directly depends on the gas flow rate, density G into height of the liquid. So in this way now the total power requirement will be Pg plus PV. So here the PT will be Pg plus PV. Now next one more term comes, that is the mixing time. How we can quickly calculate the mixing time, because this is very useful parameter for assessing the overall speed of mixing in stirred tank vessel, because we need to have the optimum time for the mixing. So it says time required to achieve the given degree of homogeneity starting from completely segregated state. So it says Tm mixing time is proportional to dt tank diameter to the power 2 by 3, a volume that proportional to rho into VL, inversely proportional to the power requirement to the power 1 by 3. In addition, tank diameter and impeller diameter ratio to the power 1 by 3. So in this way this mixing time is calculated, and this correlation has been tested for this range di upon dt in the range of 0.2 to 0.7. So for cylindrical vessel, if you consider height of liquid as diameter of the tank and volume of liquid, if I put pi by 4 dt cube, and under turbulent condition this mixing time, because you have to just put power in terms of power number, volume 4 by pi by 4 dt cube, then this term will come out to be this 5.4 divided by Ni impeller speed 1 upon Np power number to the power 1 by 3 and dt upon di whole square. So, this is very simple correlation we end up particularly for the turbulent zone. So, what is required here is Ni mixing time is, if stirrer speed is high, the mixing time will be less. If tank diameter is more, the mixing time will be more. So, typically we require the Ni and Np value to calculate the mixing requirement. So, here if we see quickly, a baffled fermenter with a tank diameter and liquid height equals 1.2 meters. So, say dt and HL as 1.2 meter. So, using a 6 blade turbine impeller and impeller diameter is di is given as 0.42 meter and stirrer speed is Ni is 1.5 second inverse. Viscosity is given 10 to the power minus 2 Pascal into second and density is given as 1000 kg per meter cube. You have to calculate the mixing time. The first is calculate the Reynolds number Re as Ni di square rho upon mu, and its value will be 2.6 into 10 to the power 4. It means this is a turbulent flow, and for turbulent flow we can calculate mixing time as 5.4 divided by Ni to 1 upon Np power number to the power 1 by 3 dt upon di to the power 2. So, Np is needed, and here I have listed the value of Np for the this type of impeller is the 6 blade turbine impeller. The Np value is 1.6 for the 6 blade. So, we can take the 1.6 value here. So, it will be 5.4 divided by 1.5 to 1 divided by 1.6 to the power 1 by 3, and what is the dt? dt is 1 upon 2, di is 0.42 square, and if you calculate we will get the mixing time as Tm as 25.1 second. So, with this I will stop here. So, today we discussed the empirical method to estimate the KLA value, and followed by we started with the mixing, what is the different component of the mixing, and then when we are doing the mixing there will be power requirement. It is important to calculate the power requirement, and further if you know what is the mixing time, and what we found that for turbulent flow the mixing time is inversely proportional to stirrer speed and directly proportional to the tank diameter. Thank you so much.